I will begin this lecture by discussing exercises 4 with you. This is on random variables, their PDF, CDF and expectations, etc. So, let us look at question 1. Consider the function f x given by c times 3 x minus x square for x lying between 0 and 4 and 0 otherwise. So, the question asked is, could f x be a probability density function for any value of c? Now, without proceeding further, you can just see that since the function can be written as x times 3 minus x. So, it will be negative for x greater than 3 and your interval is 0 to 4. So, the density function and if the sign of c you might say that we can make c negative, but then when x is equal to 2 say for example, then 3 x minus x square is positive. So, in that case again c times 3 x minus x square will become negative. So, in fact, for no value of c is the current function PDF, because it is not non-negative for all values of x in the interval 0 4. Okay. Now, we say that suppose we require the function to be a probability density function when x is between 0 and 3. So, that makes sense, because then in the interval 0 to 3, 3 x minus x square is non-negative. So, then c will be chosen as some number which is also non-negative, in fact positive, and the condition the way you will obtain c would be you integrate the given function from 0 to 3 and then the integral must be equal to 1. So, therefore, you can answer this question in this way. The question 2, the probability density function of x, the lifetime of a certain type of electronic device measured in hours is given by. So, f x is equal to 15 by x square, x greater than or equal to 15 and 0 when x is less than or equal to 15. So, that means the device is guaranteed to run for more than 15 hours. Now, find probability x greater than 30. So, again you can do it by finding out the CDF or integrating this function from 30 to infinity, right, because this says 15 by x square is x greater than or equal to 15. What is the cumulative distribution function of x, and what is the probability that 6 of such types of devices, at least that out of what is the probability that of 6 such types of devices at least 3 will function for at least 15 hours. What assumption are you making? So, here of course, you see you will assume that the devices are independent of each other and then you will do the rest by finding out. So, probability of one device functioning for more than 15 hours and then you have to say 3 out of 6. So, you can understand what all you have to do. This will become a binomial probability, where the p will be this integral from for at least 15 hours. So, will function for at least that 6 of such types of devices, at least 3 will function for at least 15 hours. So, it will be 15 and more. Okay. So, I leave it to you to do the rest. Question 3, for a random variable y, show that E y, the expected value of y is 0 to infinity, probability y greater than or equal to y dy minus 0 to infinity, probability y less than minus y dy. Actually, question 5 should precede question 3. In question 5, I am asking you to do the same thing for a non-negative random variable y. In that case, the second part of the integral will not be there, because y less than minus y. So, here in question 3, I am asking you to show that for a non-negative random variable y, E y is equal to 0 to infinity, probability y greater than t dt. So, once you show this, then you can go to question 3 and do the rest, when y can take positive negative values both. Okay. Question 4, x is a random variable that takes on values between 0 and c, that is probability x lying between 0 and c is 1. So, show that variance x is less than or equal to c square by 4. So, I am just asking you to get an upper bound for the variance, and you see the only information you are given is that x lies between 0 and c. So, all mass of this random variable is between 0 and c. Now, there is a hint. One approach is to first argue that expectation x square is less than or equal to c e x. You see, this is a non-negative random variable. Yes, it should have been said that, because 0 less than or equal to x less than c. So, it implies that c is non-negative. Therefore, this inequality expectation of x square is less than or equal to c times e x. You see, actually x square is less than or equal to c x, yes, for all values of x between 0 and c, because x is non-negative, right, and c is a non-negative number. So, from there you get this inequality when you take the expectation on either side of this inequality, and then you show the rest. So, I will not discuss the second hint. There you should think and then get the answer. Okay, question 5 we have already now question 5, the second part is that you have to obtain expectation x raised to n and show that it is equal to this 0 to infinity n x raised to n minus 1 probability x greater than x dx. So, here again the hint is that you start with e raised to x n as 0 to infinity, because so therefore, you write y equal to x n and then you will do this, and then because of the substitution y equal to x n. So, dy will be n x n minus 1 dx, and that is how you are getting this part. So, this you should be able to do. Question 6, the number of minutes of playing time of a certain high school basketball player in a randomly chosen game. So, this should be player. So, I have just cut the so that means number of minutes of playing time of a certain high school basketball player in a randomly chosen game is a random variable whose probability density function is given in the following figure. So, this is the graph of the PDF for the number of time for the number of minutes that a player in a basketball team gets actually to handle the ball in a sense, right. Find the probability that the player plays over 15 minutes. Therefore, here as remember I have told you that this probability, if you are saying that the player plays over 15 minutes, then you are asking for the probability x greater than or equal to 15. And so, here you will integrate, or you find out the, see the 15 will be somewhere between 10 and 20, you know the height of the graph at different places. So, the area to the right of 15 on the x axis, on the minute axis, that area would be the probability that the player gets to spend more than 15 minutes on the field while playing the game, right. Then similarly between 20 and 35, so between 20 and 35 the area. So, this will be the area, you can immediately find out just by looking at the graph, you do not have to do any integration or anything. So, then because anyway your this thing is not given to you, the functional form of the PDF is not given. So, just by looking at the graph you find out the area between 20 and 35, and that will be the probability that the player gets that many minutes to between 20 and 35. Less than 30 minutes, same thing. So, this will be this. So, the area to the left of 30 will be the answer, and more than 36 minutes it will be somewhere here. So, to the right. Okay. So, this was just to illustrate that how when it is convenient you can just look at the graph of the PDF and find out the required probabilities. Suppose question 7, suppose that the travel time from your home to your office is normally distributed with mean 40 minutes and standard deviation 7 minutes, right. So, the time that you would spend in going from home to office is a normal distribution with 40 minutes as its mean and standard deviation 7. If you want to be 95% certain that you will not be late for an office appointment at 1 p.m., what is the latest time that you should leave home? So, you have to read this problem at least 2 to 3 times and see that what we are asking is that you want to know the travel time which you can be sure of that time 95% of the time. That means, you have to find the probability of reaching from home to the office the time which will be possible for 95% of the time. So, here that means if x is the random variable denoting the time that you take from home to office, then x minus 40 and x we will say in minutes. So, x minus 40 upon 7 will be the standard normal variate. So, now you want to find out the probability that when this z is less than or equal to some number t is equal to 0.95. So, from the tables you get the value of t. So, corresponding value of x is 40 plus 7 into t minutes. Thus, starting time would be 40 plus 7 t minutes before 1 p.m. Then you are likely to be in the office 95% of the time on time. That means, you will be in the office by 1 p.m. 95% of the time. Okay. So, just read this problem carefully and then now, question 8, the median of a continuous random variable, this I have explained to you that the median means that half the area lies on one side and the other half lies on the other side, and I want you to find out. I think I have already done it for the normal distribution. I showed you that for a normal distribution x equal to mu is the median. So, now for uniformly distributed over a b and exponential with mean lambda, find out the median. Okay. So, this I have discussed in the class. If x has hazard rate function lambda x t, compute the hazard rate function of a x where a of a x, a is a constant where a is a positive constant. So, you can apply the formula definition of the hazard rate function and get the answer. The lung cancer hazard rate of a T-year-old male smoker AT is such that this. Now, here I have discussed in the lecture that if you are given the hazard rate function, then you can compute the CDF of the random variable, and so assuming that a 40-year-old male smoker survives all other hazards. So, we are just considering the death because of smoking. What is the probability that he survives to age 50 to age 60 without contacting lung cancer? So, I have discussed part of this problem with you in the lecture. So, you should be able to do it. Now, finally, x is uniformly this is 11th problem. X is uniformly distributed over minus 1 and 1. So, while discussing functions of random variables in the last lecture, I discussed this how you will handle probability mod x greater than half. Okay. X is less than minus half and greater than half. Then the density function of the random variable mod x. So, this should be able to do it. Question 12. The number of years a radio functions is exponentially distributed with parameter lambda equal to 1 by 8. So, that means the mean is 8. Okay. If Jones buys a used radio, what is the probability that it will be working after an additional 8 years? So, now remember this is an exponential distribution, it has the memoryless property. So, therefore, you can answer question 12 also. So, now I hope with all these hints you should be able to enjoy doing this exercise. So, let me now continue with in the last lecture I discussed functions of random variable, how you find out their CDFs and PDFs and PMFs. Now, let us talk about expectation of function of a random variable. So, if x is a discrete random variable with p x as its PMF, then we define, and g is some function, real valued function. I should have said that g is a real valued function of x. So, here g x is a real valued function of small x only, right. Then expectation g x would be, because g x itself will be a random variable, since x is a random variable, g x will be a random variable, and so this is summation I p x I g x I. So, let us see how we arrive at this form. See, the thing is that I start with you start with this summation. Then what I do is I group together all the x i's for which the value of g x I is y j, right, because g may not be a single valued function. So, here for all possible values of x i's which give me the same value of g x I. So, then I group this summation here. So, I say j here and then I am summing over I where g x I is y j. So, all those g x i's get summed up here, and then for all those gxi is yj. So, then I will write yj here, then this summation goes over all I such that gxi is yj. So, I am summing up all the probabilities pxi, all xi for which dxi is yj, right. And so, this becomes summation yj, and this probabilities they add up, because xi's are discrete and distinct values. So, therefore, you add up the probabilities and that will give you over all I such that gxi is yj. So, this becomes probability of gx equal to yj, right, of the event. This is a discrete case. So, for all possible values of xi for which gxi is yj. So, therefore, this whole thing here is equivalent to this, and so now this becomes sigma j yj. So, this is gxi equal to yj, and then probability of gx equal to yj. So, therefore, by definition this is expectation gx. So, this is your the way we define it for a discrete random variable. So, the simple formula is this, and I have tried to validate it for you by manipulating the summation terms. Okay. Then in question 5 exercise 4, you have been asked to show, I just discussed it with you. So, you have been asked to show that expectation x will be 0 to infinity, probability x greater than y when x is a non-negative continuous random variable, right. So, here we are I am just writing out this expression for the case when x is a non-negative random variable. So, now when I want to talk about expectation gx, I will do it for I will obtain this formula for when gx is non-negative, and then you should be able to take care of, because remember question 3 is your general version, where x can be negative or positive both. So, in that case gx can be also a general function taking negative positive values both, but once you understand this you will be able to do that also for the general case. So, I am doing it for gx non-negative. Okay. So, expectation gx will be using this formula, because gx is non-negative. So, 0 to infinity probability gx greater than y dy. This is I am using that question 5 of exercise 4. Then here this what I am doing is, see, therefore, see I tried to show you that gx is this function. So, now here I am separating out the integral. What I am doing is for gx greater than y, I am integrating this fx dx, right. So, gx greater, so if suppose this is your value y, then you are integrating this area, but then y varies from 0 to infinity. So, that means from here, here. So, the whole area, this whole area under gx from 0 to infinity is being integrated here, right. Then I can always change the order of integration. I can add the integrate in this way. So, that means here it will be 0 to gx. So, first of all from here I come here 0 to infinity, then from here I come x gx greater than 0, right. So, here gx greater than 0, then I am integrating this way here in this way, and then this is 0 to gx. So, your y, the integration with respect to y is from 0 to gx, and then gx is going from 0 to infinity. Okay. When gx is greater than 0, I have drawn it this way, it could be whatever it is, gx greater. So, you may start from here, or your function may be like this, does not matter. So, when you so here the order of integration, first I was integrating with respect to dx, and now I have changed the order of integration. So, when I change the order of integration, my y first varies from 0 to gx. So, from 0 to gx dy, and then my x varies from corresponding to gx positive. So, this way. So, therefore, I am taking these lines, right, and the lines corresponding to a fixed x will be from 0 to gx, and then as x varies I am integrating along these lines, right. So, this is how I am covering this area. So, this is it. Now, 0 to gx dy simply becomes gx, and then this is integral x such that gx is positive of gx fx dx. Last integral, the computation has to be for all x such that gx is greater than 0. This is equal to this. So, now it will be good if you can sit down and do it for a that means, you do it now for the negative part and then you can just add it up, right, expectation for. So, in other words, I am also telling you how to do your problem 3, first do 5, then do 3 and then you can apply it to get this result for the general function x g x. Okay. And so, now immediately you can write down that if you take a x plus b as a function of the random variable x, then the expectation will be a e raised to x plus b. Now, you can verify by writing the actual expression. That means, you can write out this expression and then show that what you get will be a into expectation x plus b. Okay. Similarly, for the variance, see the expression is a x plus b minus a e x minus b whole square and b cancels out. So, you are left with a square x minus e x whole square expectation of this. Then since a square being a constant comes out, this is a square expectation of x minus e x whole square and which is a square times variance x. So, I just handled it for this because this is very often we have already used this formula in fact. So, I thought let us formalize once we talk about expectations of random variables, then I talk about their expectations and so on in the applications. Okay. Another interesting expectation of a function of a random variable is the moment generating function, and this is very important because in the sense that sometimes it gives you extra information about the information that you can sometimes get more easily here if you know the moment generating function, right. So, let us say the definition is that m x t is the expectation of e raised to t x, right, and m x t I will write here is the moment generating function of x for all values of t for which this exists. Right. And so, some time ago I had shown you that this need not all the time exist, right. And so, whenever for all values of t for which this exists, we will say that this is the moment generating function of x. Okay. So, t is a real number. So, as t varies and sometimes for all values of t this may exist, but sometimes it may not be it may not exist for all values of t. So, for the discrete case when x is a discrete random variable and p is its PMF, then m x t will be expectation e raised to t x p x, because just now we wrote down the formula that for any function of a random variable expectation g x is summation I p x I g x I. So, I am applying this formula and therefore, m x t for a discrete random variable would be summation e raised to t x into p x for all x, the summation is over all those x for which p x is positive, right, because otherwise the corresponding contribution here will be 0. Okay. Then x a continuous random variable with f x as its PDF, then m x t will be minus infinity to infinity e raised to t x f x dx for all values of t for which the integral exists. So, the same thing, it is only defined, the moment generating function is defined for those values of x for which the corresponding expectation exists. So, if I differentiate the expression for m x t, the moment generating function for x, this is d d t of e raised to t x, and then I am taking the differentiation sign inside. And this is easy to explain, because in the discrete case, since this expression for the moment generating function, the summation is a convergent series. So, therefore, differentiation can be passed through the summation sign, right, because this is a convergent sum. So, therefore, of course, we are taking it for all values of t for which this is convergent, right. So, in that case I can pass through the summation sign, the differentiation sign. Now, if x is a continuous random variable, then it is required that this can be shown again, because it involves higher level mathematics. So, I am not doing it here. This is that if the moment generating function for x exists for all values of t in the interval minus a comma a. That means, this is some interval around the value t equal to 0, right. For some a real number, if this exists, then it can be shown that you can exchange the differentiation and integration sign. Okay. So, in case your random variable x satisfies this property that the moment generating function will exist for all values of t in an interval around the origin around the 0, then you can differentiate the you can interchange the two signs, and then therefore, when you differentiate, you take the differentiation sign inside, it will become expected value of x e raised to t x, right, because you are differentiating with respect to t. So, we will write x here, and at t equal to 0, you can see that m prime x 0 will be E x, which is the first moment, and so on. So, the first derivative of the moment generating function evaluated at the point 0 is the first moment of x, the mean or the expected value of x, right. Then similarly, if you differentiate it again, then you will get x square here, expectation x square e raised to t x, and so m double prime 0, that means the second derivative evaluated at t equal to 0 will give you expectation x square, which is the second moment. So, in general, the nth moment or the nth derivative of the moment generating function evaluated at t equal to 0 will give you the expectation of x raised to n. And so, once you have these moments, so therefore, you can make use of these things. That means, if you just compute the moment generating function, you can get the information about all the moments through this formula. So, let me now start applying the definition of the moment generating function to special random variables that we have gone through so far. Binomial random variable, the expectation value of e raised to t x would be sigma r varying from 0 to n, e raised to t r, because x takes the value r. So, e raised to t r n c r p raised to r 1 minus p raised to n minus r. Okay, this is the expression. I will combine e raised to t r with p raised to r. So, this becomes n c r p e raised to t whole thing raised to r into 1 minus p raised to n minus r. Okay. And this you can see is again an binomial expansion of the expression p e raised to t plus 1 minus p raised to n, and this exists for all values of t, right, because the expansion is valid no matter what the value of t is. So, this is, and now you see what we are trying to say is that if you get an expression like 0.3 e raised to t plus 0.7 raised to n, if you are given this as a MGF, then you can immediately say by looking at the form of the moment generating function that the value, this is the moment generating function of a binomial random variable with p as 0.3, and this is your n. So, the two parameters you can immediately find out by looking at the moment generating function, right. And if you differentiate this expression once, then see from here it will be n, derivative of this is p e raised to t, yeah, I should have said here e raised to t, right, n p e raised to t, then e raised to t p plus 1 minus p raised to n minus 1. And so, at t equal to 0, this number reduces to n p, which is the expectation of x, right. Similarly, if you differentiate this expression twice, yeah, this e raised to t is missing somewhere. So, then it should have been sum of 2. So, we will have to rewrite the expression here. Okay. So, it will be see for example, what I am doing is, so e raised to t is here. So, I am differentiating this again. So, this will be n minus 1 and p here, then e raised to t. So, e raised to 2 t, because there was an e raised to t, plus you will have to take the derivative of this, which will be n p e raised to t e raised to t p plus 1 minus p, and this whole thing raised to n minus 1. Right. In any case, when you compute this at the value t, then this becomes 1. So, you are left with n p and minus 1 p. This also is equal to e raised to t is 1. So, this is 1, 1 raised to n minus 2 is 1. Then here also the contribution would be n p. So, is it so? n p e raised to t. So, the second moment I am getting as okay, and then from here n into n minus 1 n square. So, this is not correct. So, therefore, this will be plus. So, that means here when you put t equal to 0, you are getting n into n minus 1 p square. This is okay. Then from here you will get another n p, because this is 1, and the whole thing is 1. So, this is plus n p. Now, it makes sense because you have n p. So, n square p square minus n square p square goes away, then minus n p square plus n p. So, minus, I should write out the, okay. So, minus n p square plus n p, which is n p into 1 minus p. So, n p q, this is the formula for the variance. Okay. So, please be careful when you are differentiating these expressions. Okay. Similarly, we can apply now, we can obtain the moment generating function for a Poisson random variable, and this will be expectation e raised to t n lambda raised to n into e raised to minus lambda upon n factorial, n varying from 0 to infinity. Here again I will couple e raised to t n with lambda. So, this will become lambda e raised to t n into e raised to minus lambda n factorial. So, now this is what the value of the random variable that you are taking. So, at x equal to n, and this will be if you take e raised to minus lambda outside, this is the expansion of. So, lambda e raised to t raised to n upon n factorial is the expansion of e raised to lambda e raised to t. So, the expressions may look a little complex, but handling them is not much of a problem. So, here the whole thing adds up to. So, therefore, in this case also the series is convergent for all values of t, and so that is what I am saying, if defined for all values of t, and this can be rewritten as e raised to lambda e raised to t minus 1. So, if you differentiate, so here again say for example, if I get a term, if I say that the MGF is say 3 e raised to t minus 1, then immediately by looking at this function I will say that the corresponding random variable is a Poisson random variable with mean 3. An MGF of a random variable x will characterize the probability distribution function of x. So, when you differentiate this again, so let me go through the calculations, because there might be some error again. So, first derivative of m with respect to t here would be the derivative of this would be lambda e raised to t. So, lambda e raised to t, then into e lambda e raised to t minus 1, and evaluated at t equal to 0, that gives you lambda, which is expectation of x. Second order derivative. So, there are two terms now involving t. So, the first one, the derivative is lambda e raised to t into e raised to lambda e raised to t minus 1, plus the derivative of this would be lambda e raised to t lambda e raised to t, and the same term here. Okay. Again evaluated at t equal to 0, you get lambda from here and you get lambda square from here. So, this is lambda plus lambda square. So, variance is lambda plus lambda square minus lambda square, expectation of expectation x whole square. So, therefore, this is again lambda. So, the verification, right, alternate ways of computing the same quantities. Exponential random variable with lambda as its parameter, then this will be 0 to infinity lambda e raised to t x into e raised to minus lambda x t x, and here again I couple the terms the powers of e. So, I get, so the moment generating function would be 0 to infinity lambda e raised to minus lambda minus t x dx, which I can rewrite as lambda upon lambda minus t integral 0 to infinity lambda minus t e raised to minus lambda minus t x dx. And you can see that this integral is defined for all values of t less than lambda, because this exponent must be, see this quantity must be negative, sorry, this quantity must be positive. So, that minus of this is negative, and then at infinity this will go to 0, and therefore, the integral is defined only for lambda for t less than lambda, right. For t greater than or equal to lambda, the integral does not exist. So, this is important to note, and therefore, that is what I was saying, that the moment generating function need not exist for all values of t. We have to specify the values of t for which the integral exists. Now, make the substitution to integrate this. You make the substitution y is equal to lambda minus t x, this gives you dy is lambda minus t dx, and therefore, this integral transforms to lambda upon lambda minus t. See here, this lambda I wrote as lambda upon lambda minus t into lambda minus t, right. So, to get it in the proper form. So, then lambda minus t dx transforms to dy, this is dy, and e raised to this thing is e minus y, simple integral, this is this. So, therefore, minus e raised to minus y 0 to infinity is lambda upon lambda minus t. MGF exists for t less than lambda and not t less than or equal to lambda. You can say that the corresponding random variable is exponential with parameter lambda, right. And if you do the simple verification here, derivative would be lambda upon lambda minus t whole square. There will be a minus sign with this, but then since this is in the denominator, another minus sign, and they both multiply to be positive. Therefore, m prime x 0 is lambda upon lambda square, which is equal to lambda 1 upon lambda. Okay. Now, similarly, you can compute the second order moment, and then, so that is why you know that the name is very suggestive, moment generating function. This function generates the different moments for the probability density function. Okay. Normal distribution again, it may look very cumbersome, but actually it is simple manipulation of the terms and you get the answer. So, for a normal distribution, the moment generating function would be so 1 upon root 2 pi sigma minus infinity to infinity e raised to minus x minus mu whole square upon 2 sigma square plus t x, right. You are computing expectation of e raised to t x. So, here I combine this in this square terms. So, this becomes 2 sigma square x t, 2 sigma square x t. So, I collect the x terms. So, the x terms are twice mu plus sigma square t plus sigma square. Now, I want to make a perfect square, and the reason is obvious, right. So, that the integrand part of the integrand will add up to or integrate to 1. So, you see to this I must have x minus mu minus sigma square t whole square. So, therefore, I have added mu plus sigma square t whole square to make this perfect square. So, therefore, I must subtract. So, minus mu plus sigma square t whole square, and the mu square from here is the remnant. So, therefore, this is what you have. So, this square plus mu square minus this, right. Now, if you simplify this, the mu square cancels out, you are left with minus 2 mu sigma square t plus sigma 4 t square. So, this term I have written out here as this, separated it out, and this is a constant, because there is no function of x here, x is this is dx, in fact, dx goes here, and you see that this integral in that case. Now, this is a PDF of a normal random variable, where the mean is mu plus sigma square t, not mu, but does not matter, the other things remain the same. So, this is a PDF of a normal mu plus sigma square t and sigma square. The variance does not change. This is under root of sigma square and this is 2 sigma square. So, only the mean has shifted from mu to mu plus sigma square t, and therefore, this integrates to 1, right. The PDF of a normal standard normal variate, this integrates to 1, and here you are left with just this part 2 sigma square t mu plus sigma square t square divided by 2 sigma square. So, this is it. So, when you cancel out the sigma square part, you are left here with mu t plus t square sigma square by 2. So, a simple form here again, and you can now differentiate this, and so that means let us just take the first derivative. What would be the first derivative? this is t. Yes. So, this is E mu t plus sigma square t square by 2 into the derivative of this, which is mu plus twice, so sigma square t. So, at t equal to 0, this is 1 and this is mu. So, the first derivative for the first mean, the first moment, which is the mean, right. Similarly, differentiate it again and then find out the second order moment and the variance. So, I think this illustrates quite well the concept of moment generating function and how you make use of it, and of course, that it definitely characterizes the PDFs, because by looking at the form of the MGF, you can say what the distribution would be and what would be the corresponding parameters. Then there is still more interesting applications of the MGF. This is when I talk of jointly distributed random variables, and then you can the use of the concept of independence and so on. So, all these things get connected, and I will try to show you the further properties of the MGF. So, let me now look at the moment generating function for the gamma random variable. So, the expectation e raised to t x would be 0 to infinity lambda e raised to minus lambda x raised to alpha minus 1 upon gamma alpha into e raised to t x dx, right. So, again combine this thing, and here you see t less than or equal to lambda, then only this because this is not defined unless, I mean, the whole integral will become improper if t is greater than lambda. So, therefore, this integral will exist as long as t is less than or equal to lambda, right. So, now you have this expression. So, again the trick is that I try to manipulate the integral, add, subtract, divide or multiply. So, that I get into a familiar form plus a constant into a constant. So, here you see the parameter from shifts from lambda to lambda minus t. So, that is what I will do, and that is not difficult, because this lambda I can write as lambda upon lambda minus t into lambda minus t. So, this becomes my parameter here. This is e raised to minus lambda minus t x. Now, this lambda same thing I will do, I will replace it by lambda minus t and then divide by lambda minus t raised to alpha minus 1, because this is alpha minus 1, and the lambda raised to alpha minus 1 comes out. So, you see this part is now independent of, this is independent of x. The remaining portion, all this is now the integral of the PDF of a gamma distribution with the parameter lambda minus t and alpha, right. So, instead of parameter being lambda, it is now lambda minus t for any fixed value of t, and so the parameter will change as you change, but given a value of t, then this will be the integral of the PDF of a gamma distribution with parameter lambda minus t and alpha. So, therefore, this whole integral, this thing goes to is equal to 1, and I am left with the term lambda upon lambda minus t raised to alpha, and so this is your MGF. Now, if you recall, for an exponential distribution, the MGF is lambda upon lambda minus t, if lambda is the parameter. So, what is turning out to be the exponential is gamma 1 comma lambda, that means the okay, I have been saying it out the other way. So, alpha is the first. So, that means here I want to say that this is gamma, alpha and lambda minus t, sorry. So, please the alpha comes out to be the first parameter, this is the second. So, then your exponential is 1 lambda. See, if you are looking at gamma, alpha, lambda, then for alpha equal to 1, this becomes exponential lambda, right. And here you see so therefore, now through when I have talked about jointly distributed random variables, sum of independent identically distributed random variables and so on. So, there will be a lot of interconnections that I would like to show. So, essentially what we will be deriving here is that first of all the result that if you have sum of two independent random variables, then the MGF of the sum is the product of the corresponding MGF. So, here you see applying that iteratively, it turns out that gamma alpha lambda is actually the sum of independent exponentially distributed lambda variables, exponential distribution random variables, each with parameter lambda. That means, identically, so alpha is in case alpha is an integer, then gamma alpha lambda is sum of alpha independent exponential random variables with parameter lambda. So, this is what the result will be. So, and therefore, that is what I am saying, that you will be able to show these kind of things through the help of MGFs, because here this is lambda upon lambda minus t raised to alpha, and this is alpha of them you add and they are independent, then the MGF of the sum of these alpha independent exponential random variables will be gamma distribution, because the MGF of this sum would be the MGF here, which is alpha times this. So, you multiply the corresponding MGFs when the variables are independent, and then if you are talking of the MGF of the sum, right. So, we will develop this theory as soon as I talk of jointly distributed random variables. Now, just two questions before I finish this topic, and this is x is a continuous random variable with PDF f x. Show that expectation of absolute of x minus a is minimized when a is equal to the median. So, we have defined the median for you, and here see what we are saying is that this will actually come out to be a function of a, right, this expectation, and therefore, you want to minimize it. That means, you will differentiate with respect to a, the expression that you obtain for this expectation of absolute x minus a, and then find out the critical value or the value at which this becomes minimum. So, you will have to show that it is the point at which the area under the curve is half. Okay. Now, I will just give you a hint. So, expectation absolute x minus a would be absolute x minus a f x dx, which you can like either x is less than a or x is greater than a. For x less than a, we will integrate from minus infinity to a, right. So, then this will be a minus x f x dx, because the integrand has to be positive, non negative. So, this will be a minus x for x less than a, and then a to infinity x minus a f x dx. So, the idea is that you differentiate with respect to a. Now, all of you have already done this much calculus, you can integrate. So, this will be when you have differentiation under the integral sign. Essentially, you have to apply that. Your limit is a function of the variable. I mean, you are treating a as a variable now, because this whole thing is a function of a now, fine. So, you can do this. Now, similarly, just take an example. So, let x be n mu sigma square. So, x is normally distributed with parameters mu and sigma square, and has MGF mt. Define psi t as log of mt, then show that psi double second order derivative of psi at 0 is variance x. And so, there are interesting functions that you can define through your mt. We will also be talking of the characteristic function. So, now for example, mxt for a normal is this, right. So, if you take log of this which we are calling as psi t, then this will be equal to mu t plus sigma square t square by 2, right. And so, if you take psi prime t, this is mu plus sigma square t, right, and then psi double prime t will be simply sigma square, which is, and therefore, this is also psi, because that is a constant. So, the second order derivative of psi is a constant. So, psi square 0 is also sigma square. So, this is the answer, right. And so, one can go on doing a lot of interesting things with this, and I will be developing some more results here in the next lecture.